Hey everyone, welcome back to the channel. Today we are walking through a full production style Kotlin code base. We have got a data layer, a repository, a view model, an activity, and a Compose UI, all using coroutines the right way. So let's go top to bottom. Here we have simple data models, user and post, which are default values on every field, so we can create an empty instances easily. Nothing fancy here, just our data shapes, which are data class user, data class post, val id, val name, and val email. We have here in data class post, of course, we have val title, string, and integers. Then we have field classes. This is our UI state machine. Three possible states are here, which are loading, success, and error. That's it. Nothing else can exist here. So notice we changed the exception to throwable here compared to a basic version, because throwable is broader. It cached both exception and error, more robust in production, because the compiler basically forces you to handle all three states in every when block. You literally cannot forget the error state. That's the power of field class actually. Then we have our API object. You can see here object API, funGetUsers, post, fetchData A, fetchData B. This is our fake API. In a real app, this would be a retrofit interface. Notice getUsers, getUser, getPost. These are just regular functions, not suspend. They return empty data instantly, simulating a cached or local data source. So fetchData A and fetchData B are suspend functions because they simulate network calls with a delay. So we will use these later to demonstrate parallel execution, so that you can understand it much better. And later on comes to the main part, which we have the user repository. So you will notice here that we have suspend fun, which means suspend function. This actually waits for work to finish before returning. And we have with context dispatches.io. So what we are doing here is we are pushing this work off the main thread onto the IO thread. So any network call, database read, or file operation should always be here, never on the main one. And the delay basically simulates a random network latency between 500 and 1500 milliseconds. So real world networks are inconsistent, so this reflects that. Later on we have suspend fun fetch users. This is a parallel fetch pattern you can see here, and it has ids.map async fetch user 8. You can see here for every id, this means that for every id launch an async coroutine immediately. All of them start at the same time. You just get back to a list of defaults, and .awaitAll, what it does here is that it waits for all of them to complete. So just take an example that 10 users, each taking 1 second. Sequential would be 10 seconds, so parallel is 1 second. That's the difference. If any single fetch throws like awaitAll, cancels the rest and propagates the error up. So no orphaned coroutines are there, right? As we can see, ids.map async, what we are here is fetch users and fetch user id, so it is taking it from there. Next we have private val state and mutable state flow. Result.loading, val state, state.as state flow. So what mutable state flow here is that it starts at result.loading, right? And every time we update our underscore state, the UI reacts automatically. It is a private mutable, right? Public read only, which is the UI can never write state directly. Only the view model controls the state. So this is non-negotiable in clean architecture, which we can see here. Then we have private var, fetch job and null. So what it does here is that fetch job holds a reference to the currently running coroutine. Before it starts a new fetch, it has to cancel the old one. What it does is that it prevents race conditions. Just imagine a user tapping different profiles rapidly. So you don't want an old slow request overwriting a newer fast one, right? That's what it does. And we have viewModelScope.launch, which is tied to the ViewModel lifecycle. When the ViewModel clears, this cancels automatically. What it helps is in that it has zero leaks. So now we have the state value result.loading and state value try and catch exception, right? With the if else, which has to throw an error. So set loading immediately, it spinner shows right away. Then what it does, it then it fetches success or error, and on the basis of that it updates the state and then the UI reacts on it. So now this line, pay close attention, that if E is cancellation exception, throw E, because most tutorials skip this part, that cancellation exception is how Kotlin cancels coroutines internally. If you catch it and swallow it, you break the entire cancellation mechanism. The coroutine thinks that it cancelled, but it keeps running. So always rethrow cancellation exception. Just remember, always and always. Then we have fun loader users and parallel one, right? Fun load users parallel, which has viewModelScope, state value, and then again the try catch block. So what happens here is parallel fetch for multiple users. As you can see here, the ViewModel delegates all parallelism to the repository. In simple words, that it doesn't care how users are switched in a parallel, just that they are. It just, that's all it matters, right? It is a clean separation, you can imagine. And we also guard against an empty list. So take example that if no users come back, that's still an error state. That's what it does. Later on we have to see that we have lifecycleScope.launch and repeat on lifecycle. What it does, it that it is tied to the activity lifecycle, cancels when the activity destroys, right? So repeat on lifecycle started, as you can see here. This is the important part. It should only collect the flow when the app is in the foreground. What it means is that app goes to the background and the collection pauses. Then what comes it, that app comes back, collection resumes, and it is battery friendly and no wasted work. So never collect flows without repeat on lifecycle in an activity. Never ever, right? Then we have fun fetchData lifecycle.scope.launch, valData API.get users, and update UI equals to data. So simple fetch inside lifecycle because it is safe. Because if the activity dies mid fetch, the scope cancels and update UI never runs on a dead view. Next comes is fun run parallel simulation, lifecycleScope.launch, val time, measure time, millis, which has two variables, variable A and variable B, which has awaitAll A and B, right, and log D2. So let me just explain it. This is a live proof of parallelism, right? And both fetch data and fetch data B takes 100 milliseconds each. So in sequence it would be 200 milliseconds, which is parallel. Both run at the same time, completes in roughly 100 milliseconds. And what measure time millis does here is that it wraps the whole thing so we can log and prove it. It is a great pattern for benchmarking coroutine work. Then we have the suspend fun fetch both, which is a coroutine scope that creates a child scope tied to whoever called fetch both, right? And if the caller cancels, then both async calls cancel, right? If either async throws, then the other cancels too. This is why coroutineScope beats GlobalScope every time. It has an owner, it has a lifetime, so it participates in structured concurrency. Then we have the suspend fun download, which has, as you can see, 4 downloads. All are parallel, so each stimulate a random download time, which is map, async, and awaitAll. So this what this trio does is that it is the standard modern pattern for parallel processing of a list, and the total time is bounded by the slowest single download, not the sum of all 4. And each URL logs as soon as it finishes. So you are just printing them out of order, right? which is proof that they are running concurrently. And then we have the test cancellation. So what we do here is we launch an async which immediately cancels it, then try to await it. And await, we can see here that await bracket on a cancelled deferred throws cancellation exception. We catch it and log it. This also proves that deferred extend job you can call .cancel directly on it. And to the fun part, that is Compose UI. What happens here is that it collects as state with life cycle, right? So collects the state flow only when the composable is visible, life cycle aware, right, and preferred over plain collection as state. And the when block, we can see here, when result loading, result success or result error, it handles all three states, loading, success and error, right? And then we have the cancel button which cancels cancel fetch, right, in the view model, which cancels to the running job user facing cancellation wired directly to the coroutine cancel. And because it's a sealed class, the compiler guarantees we handle every state and add a new state later, and every single when block in the app will fail to compile until you handle it. So that is compile time safety. Let me just explain it to you clearly. I know it's very messy. What it does here is that compiler guarantees we handle every state, no matter if we add a state later, and every single time when the block is in the app, it will fail to load completely until you handle it. Alright guys, so let's zoom out. What we just walked through is a complete coroutines architecture, data model, sealed class, state machine, right? So repository with parallel fetching, view model with lifecycle aware scopes and job cancellation, activity with lifecycle aware collection, compose UI reacting to state. So every coroutine has an owner, every exception is handled, every cancellation is respected, every thread switch is intentional. That's what production coroutine code looks like. If this helped, drop a like, it really helps the channel grow. Subscribe for more and comment below what you want me to cover next. Flow operators, dependency injection, testing coroutines, whatever you want. See you in the next one. Thank you.